This is the second video for section 1.1 titled Introduction to Definite Integrals. You should have an exploration sheet that says the same thing at the top, and this is also part of our informal introduction to calculus. So let's move on to number one. I'm going to give you a minute or so to read the heading here so you get the idea what this problem is about, and then we'll take a look at number one. Why don't you pause the video right now? Before we actually get into answering number one, let's take a look. One thing about this graph is that we don't have the units labeled, and we can tell that v of t is on the vertical axis and the units for velocity are feet per second. So I'm going to write that in right over here, feet per second. And of course for time, I believe that is in seconds. Let's just double check where they say that. Yes, here we go. It says a function of the number of seconds t. So let's mark on the graph over here that we have seconds. Okay, so now with number one, they are asking what does your velocity seem to be between t equals 30 and 50 seconds. So I'm going to mark that here. This is 30, here's 50, and we see on the graph what we have. It looks like our velocity is staying pretty constant there at 60 feet per second. So now the next question asks how far do you travel in the time interval from 30 to 50. So I'm going to let you think about that a little bit, and then you can check your calculation with mine. Why don't you pause right now? Okay, so if we are traveling at 60 feet per second for 20 seconds, I think all we need to do is just a little multiplication here, and we will have, I believe, 1,200 feet or 1,200 feet is how far we traveled in those 20 seconds. So the author is suggesting that the problem we just did can be represented by the area of a rectangular region, and I think that kind of makes sense. We just multiplied two numbers, so somewhere we should have, I think, a 20, right? And of course the velocity of 60 would represent the height right over here. Let's see if I can draw that in. So there's your 60. So it does appear that we have a little rectangle here between our function and the horizontal axis, and the area of that rectangle is going to be 1,200. So they're asking us to shade it, so let's see, why don't we go to, we'll shade it in red, and maybe I can do a little thicker pen here. That might let me shade it a little faster, but alright, I'll try to stay between the lines here, nothing too great. But one of the interesting parts before we move on here is our units. You know, we were actually getting an area of a rectangle but ending up with 1,200 feet. How did that happen? Okay, well, if we take a look at our multiplication, what we did, right, was we multiplied 60 feet per second, right? And that's really 60 over 1 feet per second times 20 seconds. And so we can see that our units, that's of course over 1. This is 60 feet over 1 second. So our seconds are going to cancel, and we are going to be left with 1,200 feet. And this is kind of strange because usually when we get an area, we end up in square units. But if that really kind of depends on what your units are to begin with. So since our units were feet per second and then multiplying that by seconds, we ended up in feet. So now we're interested in getting the distance traveled between 0 and 20 seconds, and that would be, you know, this area over here. I'll kind of lightly shade it. You know, if getting the area of the rectangle over here gave us the number of feet between 30 and 50, then it should make sense that getting this area between the curve and the x-axis or t-axis would give us the distance between 0 and 20. So how do we do that? Well, the author is suggesting that we count the number of squares in the region, and certainly you could estimate parts of a square, such as the example he has here. I might estimate this right here to be, say, I don't know, 0.7 of a square, maybe 6 tenths of a square, depending on how you want to do that. All right. So let me give you a chance to count the squares in the region from 0 to 20, and then we'll see if we can use that to figure out what the area is under the curve. So we'll pause it right now. I'm not sure how many squares you counted, but when I did it, I got about 28.7 squares. Looking up at number 4, the first question is how many feet does each small square on the graph represent? Well, if we look carefully, we actually are going to see that these aren't really squares. If I draw one of these right here, it appears that the units, or the space on the horizontal axis would be 5 units, and the space on the vertical axis is 10 units. So even though they look like squares, these are actually rectangles. And so we can see very quickly, of course, that 5 times 10 is going to give us 50 units. All right. So how far, therefore, did you go in time, in the time interval from 0 to 20? Well, for me, of course, if I counted 28.7 squares, then I would want to multiply that by 50. And that's going to tell me that, for my estimate, is about 1,435. And now the question becomes, what are the units? Well, if you remember what we did back in, I believe it was number 1, we ended up with feet for our units, and that should happen the same way. And I believe that's the case, because when we're multiplying the 5, we have 5 seconds here, and multiplying the 10's units are feet per second. So when we got 50, we actually got 50 feet, right? Each square represents 50 feet. And now we're going to multiply the number of squares by the number of feet per square. Okay, so this is really 28.7 squares times 50 feet per square. And of course the squares will cancel again, and we are left with feet. So it is 1435, or 1,435 feet. Okay, so there is our answer to number 4. We talked about that's how far we traveled in that time interval. Going down to number 5, they mentioned that what we did in the previous 2 problems is to find the product of the x value and the y value for a function where y may vary with x, meaning y is not constant. Okay, a product such as that is what we call the definite integral of y with respect to x. Based on the units, we did come out with feet, and we won't go into the rest of that because we already talked about it. So let's move on to number 6, where we see a similar problem, but it's got a few differences. Okay, if we read this problem carefully, we see that we have the cross-sectional area, y, which is in square inches, of a football as a function of the distance x. So, of course, that wording would tell us immediately that the cross-sectional area, which is in square inches, so I'm going to go with inches squared, is on the vertical axis, and x must go on the horizontal axis, and that, of course, is in inches that we have here. So what the author wants us to do is to estimate the definite integral of y with respect to x. So let's do this pretty much the same way we did before. Okay, you're going to count squares, and then figure out basically what the area is between the horizontal axis here and the curve here. All right, so I'll just kind of lightly shade that. You're going to get this area right in here. All right, go ahead and do that, and then you can check your answer with what I got. So pause it right now. Hopefully this time you saved yourself a little bit of time by noticing that there is some symmetry about this graph. if you'd like, you can just count up the squares that are on the left-hand side and then multiply by 2. That's what I did. I ended up counting 23.4 squares. Write that over here, 23.4, and that was on the left-hand side, and I multiplied that by 2. So I ended up with 46.8 squares there. Now, since you have to get the definite integral, we need to go a little further, right? And figure out how big is each square. And it looks like each square along the bottom is 1 unit long, but along the side is 5. So once again, these are not really squares. What we have is a 1 by 5 rectangle. So of course that's going to be, it'll be what, 1 inch, okay, by 5 inches squared. So I'm not sure if you were paying attention to units when you did this, but each square is actually 5 inches cubed. I know that seems strange. We just got an area and its units are cubic inches, but that's what this problem has given us. So now if we multiply, right, the area of each square, which is 5 cubic inches, by the number of squares, 46.8, so we'll go 46.8 times 5, I'm getting 234, and of course that would be inches cubed. And if you didn't get exactly this number, it doesn't mean you're wrong, because this is all based on my approximation of how many squares are there. All right, so let's move on to number 7. Well, we've already answered the first question to number 7, that we figured out the units are cubic inches. So what, therefore, do you suppose the definite integral represents? I'll let you think about it. Hopefully the answer is coming pretty quickly, right? If our answer was 234 inches cubed, then of course this means we just found volume. That's right, volume of the football. And in a way that should make sense. We were taking the cross-sectional area in inches squared and multiplying it by the length of the football in inches, and that gives us the volume. Now a question that's not posed on the exploration sheet, but one that I would like to ask is, how might we get a better approximation for the areas under these curves? If you think about it, counting the squares, these are pretty large squares, and we weren't real accurate with that, but we might be a little more accurate if maybe our squares were smaller, if you think about it, right? If we were to maybe cut each square in half, and I'm not going to do a good job at representing that, but if I was to draw some lines down here, and we're drawing some lines through here, and we're working with smaller squares, then we might actually get a better estimate, because we'd have less error on each square that we're looking at. Like if I outline this square, say right here, there's less error than what we were getting with the large squares. Might make a better approximation of it. And we could even make these squares even smaller than that. If we were to split that square in half, let me go with the blue, see if I can do this. Split that square in half. Now we've got even maybe a better estimate as to how many squares are in there. So that would be a way that we could actually get a better approximation. All right, so coming back now, we said the 4 big topics in calculus were limits, derivatives, integrals, and integrals. And you have now been introduced to 3 of them. Okay, remember we talked about the derivative and limits in the previous exercise, and now we've picked up one of the integrals, which is called a definite integral. Okay, and it is basically the area between the horizontal axis and a function's curve. Now, of course, in geometry, you learn how to determine the areas of regions defined by regular shapes. But if we take the limit of these areas, okay, and there's that word limit, that's kind of the key here. This is what makes it calculus. If we take the limit of these areas as the measurement regions get smaller and smaller, then we have a definite integral. Okay, so thinking about that, what we were talking about, if we got 234 cubic inches. Now, if we use smaller squares on that last problem, maybe we would get something like, 234.5, and then if we use smaller squares, we might get 234.556, and if we use smaller squares than that, if we keep doing this, we're going to be seeing that our numbers are heading towards some limiting value. And that's what we mean. If we were to take the limit of these areas, okay, as the measurement regions get smaller and smaller, then we really have what's called a definite integral. All right. And of course, as we have seen in these two explorations we've done, that both derivatives and definite integrals, as well as pretty much all of calculus, are based on this idea of a limit. That's what makes it calculus. So we must first understand limits before we learn about other topics, and limits are going to be what we study in Chapter 1. So we'll see you in class to talk about this.